Hey, what's up? It's Miss Wesley on to our next polar unit lesson. And here we're actually going to backtrack into a little bit of chapter 6 and speak of the complex plane and complex numbers in polar form. This has been a unit where converting has been a big deal, and we've mainly been converting between rectangular form in terms of x's and y's and polar form in terms of r's and thetas. But now you'll see us using some of those same conversion skills just in a different format. At the top here, we've got a little conic section warm-up. I actually want to skip down on page 12 of the polar packet to the middle of the page where we see a picture of the complex plane. And you might be wondering, Miss Wesley, I thought you were going to start with a joke, and I was going to tell you a construction joke, but I'm still working on it. All right, let's look at this picture. My eye gets drawn to this visual where I see some complex numbers. I know complex numbers in standard form. Taking the form, and I'll fill it into this blank here, a plus bi. A and b are just real number coefficients. Every complex number in standard form has a real part, the a, and an imaginary part, the bi. And you can see that we can actually graph this on what's called the complex plane. So I want to get used to just like figuring out how to plot numbers that are given in the form a plus bi. It says the point AB can show you where the point would go around the complex plane. So for instance, 3 plus I has an a of 3 and a b of 1. You're going to go over 3 positive on what's called the real axis. So I'm going horizontally positive 3, and you're going up vertically on the imaginary axis 1, which is the coefficient in front of the I. In the complex plane, the horizontal is going to be dubbed the real axis, and the vertical axis, like you see on the picture, gets to be the imaginary axis. So you'll see another point that's plotted here. The point negative 2 minus I refers to go negative 2 on the real, go negative 1 on the imaginary, and you land down in quadrant 3. There's a couple other things with this that fall in section 6.5. The absolute value. This you might have been introduced to very briefly in like an Algebra 2 course. The algebra 2, or the absolute value or the modulus of a complex number, those two terms are synonymous, just refers to the distance that it takes you to get from the origin to that point. So I could actually visualize it on the graph. If I wanted the modulus or the absolute value of this point over here, I'll draw a dotted line from 0, 0 over to that point. Finding the absolute value is as easy as just finding the distance of the line that I just plotted. So I'm going to use that in this definition. The absolute value of a complex number, z, we're calling it, a plus bi, would have this notation with absolute value bars around it. And I would just use Pythagorean theorem or the distance formula, right? Square root of how far you traveled horizontally squared, so a squared, plus how far you traveled vertically squared, b squared. I saw a tweet the other day. Somebody said they went another day without using the Pythagorean theorem, and they were blaming it on their math teacher or something. So here's us using the Pythagorean theorem. It's been coming up at a lot of random times throughout this year. Okay, so some real, just basic examples that you see at the bottom of page 12. It says to plot and find an absolute value, just getting our feet wet with the format of this. So I've got my complex plane. Can you pick a quadrant where this point is going to fall? Well, it would be nice if you picked out A and B. So A is negative 2. That's how far you're going to go horizontally. And B is going to be 5. So we would go up vertically. I'm thinking we're going to land in quadrant 2. Let's go over to negative and up 5. 1, 2, 3, 4, 5. I'll put a dot here, and that's where the point falls. Find its absolute value. No big deal. I could just sketch out that distance. And I could use the formula above or just think Pythagorean theorem for this one too. So let's give that a try. Absolute value of the complex number z equals the square root of a squared plus b squared. So negative 2 squared gives me 4 plus 5 squared gives me 25. The modulus or absolute value, the distance from the origin to this point, square root of 29. Some of these, you're going to see some today that might just pop into your head. You might be able to guess the absolute value of this number without doing much computation. What quadrant are we in? We're over 3 positive, we're down 4 negative. We've got a point in quadrant 4. So there's the point z, 3 minus 4i. What is its modulus? I wonder if you could look and visualize a right triangle here. That is a 3, 4, 5 right triangle. That should do the trick. So since it's a 3, 4, the hypotenuse should be 5. I'm going to say the absolute value of z, or the absolute value, if you want to write it as 3 minus 4i, gets to be called 5. And that is the square root of 3 squared plus 4 squared, if you wanted to show the work. Fine. Now we move into section 6.6 a little bit too. Again, a lot of this is just like basics, vocabulary, and how to convert back and forth. But we're starting with a little intro on page 13 of your book calls it trigonometric form, and I like to call it polar form. You can call it either one, but trig form or polar form is always going to have to do more with r and theta than rectangular form would with x and y of a complex number. Now that we went through that whole discussion, this warm-up should be a cinch, just plotting where these points should go. If you want to just real quick to test yourself out, figure out where you would plop A, B, and C. A, I'm going to go over 2 positive and up 3 on the imaginary. Let's put an A up in quadrant 1. Then B looks like quadrant 2. You've got a negative x, negative 3, and you've got a positive amount of distance you have to travel on the imaginary axis, up 5. So 1, 2, 3, 4, 5. According to what we just talked about, that should flow there. How about C? Both negatives. Negative 2, then go down 4. Whoops, I didn't go quite far enough. This is going to be C. And we could, if we needed to, easy distance formula calculations would give you all of the absolute values of those complex numbers. Can we go the other way around? Name each point, graph below as a complex number. I want you to get used to the fact that you could be given a rectangular point in ordered pair form. So 3, 2 would tell me exactly where to go, and I'd be plotting that point. From here on out, if I give it to you in this form, if I say 3 plus 2i, I want to get used to the fact that this complex number still lands you in that exact same slot. So whether I give it to you this way or that way, we are referring to this point in quadrant 1. Here you've got negative 5, 6 in ordered pair format. That's just like saying as a complex number in rectangular form, negative 5 plus 6i. So what I'm getting at is I was using the letters A and B a lot on the last page for those 2 coefficients, your A and your B. And we will use them on this page too. You're about to see them in the box that we look at next. But I also want to think about this as really relating this number to the x value that's given in the original ordered pair, and relating this coefficient, the 6, to being the y value as well. So we've got a little bit more with converting under here. It says trig or polar form, those are synonymous, of a complex number. And I don't actually have to tell you anything new. Nothing in this box is new news. As you glance down at each of these equations, we've actually been using them with x's and y's throughout the entire unit. But how would we convert? So let's say I'm going to relate the a and b to x and y, and I'll say I start in rectangular form, and my complex number is x plus yi. And I'm looking to convert this using facts from trigonometry that I already know of. So this is rectangular form. Well, someone tells me I need to convert to polar. I say no problem, because I know that x equals r cosine theta, or a, and then y or b is going to equal r sine theta. So can you do those plugins for x and y here? Instead of x, can you write r cosine theta? We're pretty used to that. And instead of y, we're writing r sine theta. And the difference here is, with this format, it's not just an x comma a y to denote the point, it's an x plus yi, and that's how you can show it. Now, in general, we clean this up a tad. Most mathematicians say, why write the r 2 times when you could just neatly factor it out to the front? So here's your standard form of a complex number in polar or trigonometric form. It's r parentheses cosine of theta plus I sine of theta. And you're going to see over the next couple lessons that we're using this polar form a whole lot. It is often that either the problem starts like this or it ends like this, because we're trying to convert, from polar to rectangular for these complex numbers. And we write this so often, and it gets so cumbersome, that we created, I actually got this from an old textbook, but it was created, and I'll let you guys leave your answers like this, an acronym or an abbreviation for r cosine theta plus I sine theta, and we call it CIS. I bet you've never heard of it. So it's r CIS theta. I want you to circle that. You can write, that's an abbreviation, like that. The CIS is not a coincidence. It stands for cosine plus I sine. That's where the CIS comes from in that abbreviation that I just wrote. So what you'll see that's cool is, and I'll show you with the problems below, if you feel like not writing this whole thing out, this is a completely acceptable way to leave a polar number in complex, a complex number in polar form. Okay, so all this is old news, just with A's and B's instead of X's. The number R, we use this term on the last page. R is called the modulus, right? On the last page, we referred to the modulus as the absolute value, right? The distance from the origin out to the point. Doesn't that sound like R in polar form? That's your radius, right? If I'm going to this point here, my radius out from the origin is going to be called the modulus there. And theta, just to give it a technical term, is an argument. An argument of z, an argument of that complex number z in trig form. Now I want to try converting with you. This is where things get a little bit more fun. Convert the complex number to from standard rectangular to polar form. We've done this before, but it was in a different format. I would give you an ordered pair, and you would convert that ordered pair. Well, this shouldn't be a new skill for us. If we can convert to polar. We just want to leave our answer in a different format. So I'd say step one, can you figure out a quadrant for this? 1, 2, 3, or 4. We'll relate this to your x's and y's. Your x is going to equal -2, and your y is going to equal -2 square root of 3, right? And that'll help tell me where this thing is going to land. It should be down in quadrant 3, where I'm negative on the x-axis, negative down on the y-axis. So keep that in mind as we do the whole problem. Now I'm going to use the same exact equations I used from converting before to convert here. Let's get R first, since we're interested in getting polar form. Well, R equals the square root of x squared plus y squared. That comes from Pythagorean theorem. So x squared is 4, and then plus y squared, it's going to be 2 squared of 4 times square root of 3 squared, which is times 3. You're going to end up getting the square root of 4 plus 12. And R, in this problem, you could actually answer this with a positive or a -4. I'll put that outside of what I circled, but there's a way to answer this problem in either way. What about theta? As long as we make this land in quadrant 3, and that'll come into play here, I'm going to be satisfied. So tangent of theta, always by definition, equals y over x. Always has, always will. So -2 square root of 3 over -2, and those can cancel. Does this ring a bell? I gotta think, and this is great exact value practice. I have to think of an angle. I would love for it to be in quadrant 3, where the tangent's positive, to land me in the right spot, where the tangent would be square root of 3, and if you think about it, your reference angle needs to be pi over 3 for this. I'm gonna say pi over 3 would have been a good quadrant 1 answer. How about 4 pi over 3 for a good quadrant 3 answer? Last, this might be the most important part of the process because this is the only new part. Nothing else we've done is very new. How you leave your answer is kind of new. So we're going to write it as r cosine theta plus I sine theta. That's the notation for a complex number in polar or trig form that we used above. So r is 4. I'm going to use positive 4 to land me in quadrant 3. We'll say cosine 4 pi over 3 plus I sine of 4 pi over 3. I don't know about you, I've been having trouble writing on this computer program. I feel like my handwriting's so sloppy, and it was a lot to write. This is a fine solution. This is the full-out answer to number 1. Here's your abbreviation. Feel free for me. Now, WebAssign doesn't know this notation, so WebAssign might not accept it. I'm going to write, if I'm just writing on paper for shorthand, I'll use the abbreviation CIS and then 4 pi over 3. Again, this answer is not unique. I could have probably chosen -4 as a radius and just used pi over 3 as my reference angle there too. So there's many, many ways that you can leave an answer in polar form. Let's try number 2. Think of a quadrant first. Okay, let me move myself out of the way. I'm running out of room here. And we are over 6 on the x-axis, and we're down 6 on the y. So we're down in quadrant 4 with a positive x and a negative y. Because those two values were both 6s, a 6 and a 6, I wonder if just looking at this picture for number 2, you can tell what the reference angle is going to be already. I want a quadrant 4 angle where the x and the y would be the same, meaning the tangent of theta would be, what is it? This is -6 here, -6 over 6. So what would be good for an angle where the tangent would be -1 and you're down in quadrant 4? I'm thinking 7 pi over 4. Let's use that as our theta. How about r? Well, r squared equals the square root of x squared plus y squared, or a squared plus b squared. 36 plus 36, 72. R can be simplified as 6 squared root of 2, and we can leave that as r cis theta. So 6 squared root of 2 cis, 7 pi over 4. Stay tuned as we learn to convert the other way. See you soon.